Welcome to the Crazy Hat Chemist. So another video here on kinetics. So let's get started. Bam! So today we're talking about the kinetics calculation number two. Okay, sugar fermentation occurs according to the following rate law. R is equal to K, concentration of sugar to the first power. We already did this one. You do know that this is first order kinetics because this order of this reaction is first, because the exponent is a 1. That's why it's first order. Okay, and an associated rate constant of K is equal to 3.3 times 10 to the negative 4 per second. Okay, we did do this already. There's the integrated first order rate law. Okay, beginning with 10 grams of sugar, how much sugar remains after 2 hours and 20 minutes? So, okay, it's first order kinetics. We got our rate constant, we got our integrated first order rate law, and we have our initial concentration of 10 grams of sugar. And we have our total time. Our total time is 2 hours and 20 minutes. Okay, so this table method works, and I'm going to show you first. I'm going to show you two different methods here on problem 2. Coincidence? I think not. Okay, but I'm going to show you a table method, and this table method only works when you are dealing with whole half-lives. So you need to make sure that you're dealing with a whole half-life if you're going to use this table method. Okay, so our total time here is 2 hours. I'm going to convert the 2 hours into minutes. So you should see that the hours cancel out, and it's for every hour you've got 60 minutes. So now you've got, for 2 hours, there's 120 minutes. That's equal to the 2 hours. But there's an additional 20 minutes. So it's 120 plus the 20 minutes of additional time beyond the 2 hours. So that equals a total time of 140 minutes. Okay, that's our total time, is 140 minutes. So T of 1/2 is 2100 seconds. We solved that on the previous lecture. So you need to look at kinetics, a kinetics calculation number 1 to get the 2100 seconds. We're going to convert this now into minutes. Why into minutes? Because my total time is in minutes, so I want to have the same set of units for time. That is the total time and the half-life time. They're both in minutes. Okay? All right, so here's our table method. So on one column, I'm going to have the number of half-lives. On the middle column here, I'm going to have the total amount of time. And the far right-hand side, I'm going to have the mass remaining at that total amount of time, given those number of half-lives. So you're going to start off with 0 half-lives. The total time is, of course, 0 because you actually haven't started. That means this is the beginning. And what do you have initially is 10 grams. Okay, because that's what it said at the very beginning of this problem, is that you start off with 10 grams, and that is at the beginning, so that's time 0. So how do we fill out the rest of this data table? That's what we are interested in here. So for the time, we're going to add a half-life amount of time for every half-life that we have. So we determined that the half-life time is 35 minutes. So we're going to add 35 minutes to the previous time, which was 0. Then we're going to take the amount that we have and we're going to divide it by 2. That is, for every half-life, half of it remains in the next time frame. So that's what we've got. Now the number of half-lives, we're going to add 1 each and every single time. Hopefully I didn't need to write that down. So in one half-life, which takes now 35 minutes total, how much is remaining of the 10 grams? Now you have 5 grams remaining. So we got to figure out, is this the total time of 140 minutes? No, this is a total time of 35 minutes. I need to add up this column here until I get to 140 minutes. So I'm going to add up another 35 minutes. I'm going to divide the amount that I had at the last step by 2. I'm going to add 1 to the total number of half-lives. So the total number of half-lives now will be 2 half-lives. I have added 35 to the 35 that I had before, so now I have 70 minutes. And I have divided the 5 grams by 2. That gives me 2.50 grams remaining at 70 minutes, which is corresponding to 2 half-lives. The 70 minutes still does not correspond to the 140 minutes that I'm looking for in this problem. So I need to keep on going with my table. In 3 half-lives, I'm going to add 35 minutes to the 70 minutes. Now I have a total time of 105 minutes. I'm going to divide the 2.50 by 2, and now I have 1.25 grams remaining at 3 half-lives. The 105 minutes still does not correspond to the 140 that I'm looking for. At 4 half-lives, I'm adding 35 to the 105, so now I have my time frame that I am looking for, which is 140 minutes. I've divided the 1.25 by 2, and I get 0.625 grams. And this is the amount remaining at 140 minutes. It takes 4 half-lives for this to occur. So this is kind of like the table method, and you just slice it in half or add the amount of time necessary for each half-life. Pretty simple. Okay, it can be very tedious, especially when you have a large amount of time or a large amount of half-lives, and there are many possibilities for error here. Okay, here's another method, and this is actually my preferred method every single time, and that is to use the integrated first order rate law. We already know the integrated first order rate law. We know this is first order kinetics, so why not use the integrated first order rate law? So what do we know? Okay, we know the rate constant, so we know K, all right? We know the initial concentration, which is the initial amount of sugar in grams. Okay, we also know more information here as well, okay, and that is the total time. Now, we do know that K, that is the rate constant, that is 3.3 times 10 to the negative 4 per second. Okay, so we know the rate constant in seconds. We need to get the total time now in seconds. So what I need to do is solve for that 2 hours and 60 minutes and now convert that into seconds. So I've already converted it into minutes. Now I just have one more step to convert those minutes into seconds, and that's what I'm going to do next. So that's what I've done right here. I've converted the 140 minutes into seconds, and now I have 8,400 seconds. So now you should see that my total time and my rate constant have the same set of units of seconds or per second, so that the time units cancel out. That's critical. That's one of the very first steps that you're going to do here. Then the only other part that I am having to plug into the integrated rate law is the amount that I have initially, which is the 10 grams. And then I'm solving for the amount at time t. All right, so let's see if this plugs into that integrated first order rate law. So I have natural log of x of t divided by 10 grams, that's the x of naught, equals negative 3.3 times 10 to the negative 4 per second, and that is my K. I got my 84 seconds right there multiplied by the rate constant, and you should see that the units of time cancel out. I did mention that before, but this is the time that you're going to pause and make sure that your units of time cancels out. Now we're going to rearrange this a little bit, solve for that multiplication problem on the right-hand side, get rid of the units of time, and we're going to separate out that natural log problem with a subtraction problem because it is a division problem. Okay, and you should see that this is where these numbers are coming from. I've already described the rate constant and the time. So natural log of x of t is minus natural log of 10 is equal to negative 2.772. So now what we have to do is we need to get the natural log of 10. So you're going to get your calculator out, plug 10 in there, hit the natural log button, and bam, you're going to get a number. Okay, that number is 2.303. Okay, we're still solving for x here. So we're going to move that negative 2.303 to the right-hand side by adding 2.303 to both sides, and this is what we get. So we get natural log of x is equal to negative 0.469. So the question is, how do we get rid of that natural log in front of the x, because we are solving for the x here. So you should see that there's on your calculator the toggle back and forth. So it's just like a multiplication division or addition subtraction. There is an opposite function for each. What's the opposite function for the natural log? And that's e to the, and that's a lowercase e, and that's right here. So I'm going to take e to both right and left hand sides. And so I'm going to get e to the natural log of x. That will wipe out the natural log. I'm going to have x is equal to e to the negative 0.469. And what does that equal? X is equal to 0.625 grams. Now you should see that that was the answer that we got from the tabled value. It took me a much longer time to explain it using the integrated first order rate law. But the integrated first order rate law, the beautiful thing about that is that it will work with any time frame. It does not have to be a whole number of half-lives. Okay, so the tabled value only works with a whole number of half-lives simply. But the integrated first order rate law works all the time, and that's my go-to. Okay, so please use the integrated first order rate law. That was kinetics problem number 2. I hope you enjoyed that. And I got another crazy hat here from you. I got this from another teacher colleague who has since retired. I'm hoping you're having a great time in retirement. But thank you very much for the Cisco hat. Love this hat. Woohoo! Give me a thumbs up if you like that video. Subscribe to my YouTube channel. Find me online and find my website. It's pretty awesome. Thanks to my son. I'll see you next time. Bye for now.